Now I would like to request Mr. Chakravorty sir from EC department to please felicitate Dr. Sivaji Chakravorty sir of Jadavpur Engineering Electrical Engineering, Jadavpur University Electrical Engineering Department. It is a privilege to felicitate sir. Sir, please be on the stage for the felicitation. Thank you, sir. Thank you. I would like to request Mr. Deputy Chakravorty sir to please speak the auditorium. Sir, Sivaji sir, it is not yet over. Sir, Deputy sir, please felicitate sir for the auditorium. Thank you for the felicitation session. So now we are going ahead with the program for the one-day seminar. So for that, I would like to first introduce Dr. Sugata Munshi sir, who is going to be delivering the first informative session for today's seminar. Dr. Munshi sir is a retired professor, Electrical Engineering Department of Jadavpur University. Sir has completed his BEE in 1980, AEE in 1985, Jadavpur University. Sir has worked in Plasma Physics Department of Shaha Institute of Nuclear Physics from 1985 to 1990 respectively. Sir has visited Japan in 1986 and had training at Heavy Engineering Works of Toshiba Corporation. Dr. Munshi sir joined Electrical Engineering Department of Jadavpur University in 1990 as a lecturer. Dr. Munshi has been awarded for Outstanding Career Award 2022, awarded by IEEE Signal Processing Society, Calcutta Chapter. Some of the other notable awards of Dr. Munshi sir, along with his other colleagues, include President of India's Prize, Pandit Madan Mohan Malviya Memorial Prize, Thomas Watt Memorial Prize, Tata Rao Medal, and 2 certificates of merit awarded by the Institution of Engineers India. Sir has authored and co-authored 60 research papers in international and national research journal and about 35 papers in conference papers. Sir holds 2 Indian patents jointly with other colleagues. Co-guided 6 PhD theses and about 40 master degree theses. Sir domains of interest include signal processing, sensor systems, and intelligent instrumentation. Now I would like to request sir to please be on the stage and to please start the session. Thank you sir, thanks a lot. And it will be an honor for us to have an experience of being a part of the session.
सर माउस की लागते हैं আমরা তাহলে অ্যারেঞ্জ করব
Hello. Thank you for putting. না ঠিক আছে কিন্তু এটা খবর নিয়ে আসতে হবে good afternoon to all of you. It's my pleasure to be present here on this occasion. I understand that most of the audience, they are first year and second year students. So what I have selected is that a topic on electrical sensors. Many of the things, they are known to you perhaps. I will not go into any complicated details. Alright. I'll try to share with you some of the very basic topics. Now sensors, they are devices or components through which we can connect with the physical world. You have perhaps come across the term cyber physical system. If you go to the internet, you will find that there are master's degree courses, even UG courses with subject cyber physical systems. What do these cyber physical systems stand for? Whenever the word cyber comes in, people think that it has something to do with internet. That is not a proper conception. Cyber physical system is very simple. You are aware of systems, isn't it? Can be an electrical system, can be a mechanical system, can be a thermal system. Whenever you integrate a computer with a system, it becomes a cyber physical system. Well, it's also true that nowadays, every cyber physical system, it will have capacity to interact over networks, interact over Internet of Things, etc. But so far as definition is concerned, cyber physical system does not mandatorily imply that internet has to be there. Alright. So these cyber physical systems, they get a feel of the physical world through these sensors. The input to these sensors, they are physical variables like temperature, can be acceleration, can be displacement, can be humidity, can be other things. Alright. So these things, these physical variables, they are converted into electrical quantities by these sensors. The sensors only cannot do this. The sensors have to be placed in some electrical or electronic circuit. And the ultimate output, which I am representing here by Y. So X is the physical variable that I want to measure. Y is the ultimate output. In the most common form, Y is the voltage. In certain cases, it can be frequency of a pulse train, etc. Alright, in certain cases it can be a current signal. Now, I have shown here what is the desired characteristic between the output Y and the input X. It should be a straight line with zero slope, zero intercept. Alright, that means Y should be proportional to X. Why is it required? Second possibility is that Y will have a linear relation with X, but there will be an intercept. That is not a problem because we can easily remove that intercept, the offset, the so-called offset. Alright. Now measurement, it can be of two types. One is static measurement. The temperature say it's remaining constant and you are measuring it. You are reading the display of the temperature value. Another type of measurement can be dynamic measurement. What is this dynamic measurement? The physical variable, the temperature or the pressure, it is changing with time. And in that case, you want to record the pattern of variation of the physical variable with time. So, if the temperature or pressure, if it is represented by X, it is changing with time, we desire that the output Y also will change with time in the same manner. So, we will be able to detect. So, it is desired that the transducer means the sensor together with the electrical and electronic circuits. It should have a gain of K. If we have some idea about signals and systems, we desire that it should be a zero order system. Alright. In that case only, the output YT, it will be an exact replica of XT. But you know that it is not possible in practice. But we have to try that the relation is maintained as far as practicable. The first type of sensor that I have considered, they are resistive potentiometer, very simple sensors. They are simply You know about rheostat. The same configuration, two fixed terminals and a wiper. This is a displacement transducer, a displacement sensor. The object whose position or whose motion you want to study, that object is mechanically coupled. As you can see here, that object is mechanically coupled to the wiper. That box, it represents the object in motion. It's mechanically coupled to the wiper. The resistive potentiometer is fed from a DC voltage source, and the output voltage EO, it gives a measure of the position of the object X. EO is proportional to X. Because EO is proportional to X, the pattern in which X will vary with time, it will be same as pattern of variation of EO with time. Same thing. Alright, so our purpose is served so far as dynamic measurement is concerned. In many cases, it is desired that when the object under motion, it just crosses a certain threshold, some input will be triggered on. Just an arbitrary example. In certain cases, you will find that the object, position of the object, if it crosses a threshold, some motor will be turned on, some pump motor will be turned on. How to do that? I have shown here the threshold by this dotted line. So what will happen? When this threshold is crossed, EO will exceed a certain value. What is the circuit possible? Here I have considered a comparator. So VTH is the voltage, the value of EO when the object just reaches the threshold. So whenever the voltage EO crosses this voltage VTH, the output VO, it will become high. Otherwise it will become low. VO becomes high means a signal is sent to the motor circuit, turn off the motor. Alright, so a pump will be turned on, some water will be filling the tank, like that. These resistive potentiometers, they can also be employed for measurement of pressure. I have shown here one elastic element that is used for primary sensing of pressure. What is that? I have considered here bellows. Bellows are made of materials that have good elastic properties. As for example, stainless steel, beryllium, copper, phosphor, bronze, etc. So these bellows, they are hollow. One end is closed. The upper end is closed. The lower end is open. So the pressure of the fluid that we want to measure, that fluid flows into the bellow. The open end is fixed in position and the closed end is free to move. So what happens? Under the action of the pressure differential, the bellows either compress, either they squeeze or they elongate. As a consequence, because the bellow is mechanically coupled to the wiper of this resistive element, the resistive potentiometer, what will happen? Because it is fed from a DC voltage source VR, its output EO will change. EO will be taken to some voltage measuring device, isn't it? So that voltage measuring device can be calibrated in terms of the pressure differential. So you get a simple pressure gauge, as simple as that. In this case, one important disadvantage is that the voltage source VR, it has to be very, very stable. Otherwise, there will be error. You can easily understand. Alright. So how to overcome this problem? You may say that we'll have a very stable source. That increases the cost. And even with very stable source, there is temperature dependence due to which VR will change. So what's the way out? We come to that. Here I have shown a level gauge. A float. You have seen a float floating on a liquid. Alright. Coupled to this float is the wiper of a resistive potentiometer. The resistive potentiometer is supplied from this constant voltage source VR. The output voltage EO is measured by a voltmeter. As the liquid level rises, the float position rises, and what happens? The wiper slides in this direction, the voltage EO increases. So the voltage measuring device to which you have taken VEO, that can be calibrated in terms of the liquid level. Remember that this float-based instrument, it can also be used for measurement of level of a solid. But in that case, the float has to be very light, very, very light, so that it doesn't change the level of the solid. Now come to the problem of the variation of the supply voltage. Just see here, if many of you do not have any idea about the functioning of ADC, just see here, you have to accept this fact. What does this analog to digital converter do? ADC stands for analog to digital converter. What does this do? The output of the analog to digital converter is a binary word. A word that is encoded in terms of binary numbers. But that word, it actually represents a decimal number, which is this fraction input voltage by V reference. And as input voltage to this ADC, we are using this VR. So what does the output of the ADC represent? Fm equal to EO by V reference. That means EO by VR comes out as X by XP. XP is the total length of the resistive potentiometer. X is the length that is covered by the wiper. So nowhere in this expression VR appears. So we have been able to get rid of VO. So even if there is fluctuation of VR, what will happen? It will not affect the performance. Alright. Now come to another type of resistive gauges. These are called electrical resistance strain gauges. They are meant for measuring strain and other physical quantities that can be converted into mechanical strain of some elastic member. So what does it consist of? It again consists of a resistive element. That resistive element is fixed onto the mechanical structure whose strain is to be measured. I have started. So this strain gauge, a resistive element mounted on some epoxy backing, and that attached to the cantilever or whatever may be the mechanical structure by means of some appropriate adhesive like nitrocellulose cement. So if that is the case, if there is proper bonding, the strain that takes place in this structure, in this object, it will be faithfully transferred to the resistive gauge. Here I have just started from the basic expression of R rho L by A. If you differentiate both sides, you will get an expression of this form. dr by R divided by epsilon. This is called gauge factor. It's a property of this strain gauge, the resistive element. So this is 1 plus 1 by epsilon. d rho by rho, you understand rho is the resistivity, minus twice 2 by epsilon dd by d. Just maneuvering, mathematical maneuvering. So gauge factor, which is the measure of the sensitivity of this gauge, comes out as 1 plus 2 mu, mu is the Poisson's ratio, plus 1 by epsilon, epsilon is the strain, d rho by rho. Now just, if I ask you the question, due to mechanical strain, don't say that due to temperature the resistance value will change. It will change. I am not going into that details, that part. Due to mechanical strain, what will happen to the gauge so that its resistance changes? Obvious answer will be due to mechanical strain. What will happen? The dimension of the gauge will change. Alright, the length will either increase or decrease. The cross section will either decrease or increase, thereby changing the resistance. Well, that is true, mostly true in case of the metal alloy gauges. Metal alloy gauges, for them, it's mostly true. But what is not appreciated in many cases is that the resistivity also will change. That is, change in the resistivity due to mechanical strain, it is very small. Alright, in metal alloy gauges. But in semiconductor gauges are available. Alright, in semiconductor gauges, the most large change in the resistivity, that will changing the resistance due to mechanical strain, it will come from changing the resistivity. So if I compare the gauge factor of metal alloy gauges and the gauge factor of semiconductor gauges, just see in case of metal alloy gauges, the gauge factor is around 2 to 6 at most. But for Semiconductor gauges, what happens? The gauge factor ranges from, it can be minus 140 to plus 175. Extremely high, extremely high. What's the significance of negative minus 140? In case of metal alloy gauges, due to change in the due to mechanical strain, due to tensile strain, the length will increase, the cross section will decrease, so the resistance will increase due to mechanical tensile strain, tensile force, and due to compressive force, the resistance will decrease. But for semiconductor gauges, it's not mandatory. For N-type gauges, the reverse will happen. The reverse will happen, alright. Even if there is elongation, tensile stress, due to that, resistance value will not increase, it will decrease. That's why this minus 140 has come in. So semiconductor gauges are therefore very good compared to the metal alloy gauges, but there are problems, of course. Alright. Problem with semiconductor gauges, although they have very pronounced merit compared to the metal alloy gauges, is that the relation between delta R by R and epsilon, it was constant in case of the metal alloy gauges. Here it's not constant. Alright. Here it's a non-linear function of epsilon. Now see, whenever we design a resistive sensor, what we want, the change in the value of the resistance, it should have a linear relation with the physical variable. And we should place that sensor in some circuit so that the output voltage has a linear relation with the change in the resistance. So that ultimately the output voltage has a linear relation with the physical variable X that we are measuring. So here, because the relation between delta R by R and epsilon is non-linear, what will happen? It will be a problem, a demerit. Alright. Now here I have considered a single gauge mounted on a cantilever. Under the action of this force, the cantilever flexes, the resistance of this metal, I am considering for the time being metal alloy gauges, so apparently the resistance will increase. So this is the bridge circuit. Remember that the strain gauge mounted on this cantilever, it is at the site. Your other arms of the bridge circuit, your measuring device, your supply, all these things, they are in the control room. So connections through a cable have to be taken from the strain gauge to this measurement circuit through a cable. I have considered 3-core cable. Alright. Because if you consider 3-core cable, one of the cable core will lie in one of the bridge arms, another cable core will lie in the adjacent bridge arm. So the effect of RL getting introduced into the bridge arm, that effect will be lessened to a certain extent. It will be lessened. It will not be removed. It's there. So because these lead resistances have crept into these bridge arms, what will happen? Lead resistances, their resistance will change throughout the day. Throughout the ambient temperature changes throughout the day, starting from morning to deep in the night. So that gives rise to error. And remember, why is temperature dependence of the gauge? Remember that the temperature dependence of the resistance gauge is there. We want that the resistance gauge, its resistance should change only due to mechanical strain. The temperature shouldn't have any effect. But because it's a metal alloy gauge or semiconductor gauge, the resistance will also change due to temperature. So here temperature will also give rise to error. Temperature dependence of the gauge resistance itself, the temperature dependence of the connecting leads, they will be there. For the sake of lessened accuracy, if the site and the control room, they are very close, we can ignore RL, the lead resistances, the core resistances for the time being. With ignored RL, the relation between VO and this delta R by R, just see that VO will be delta R by R 1 by 1 plus delta R by 2R. So here we desire that the relation between VO and delta R by R it should be linear. Alright. If relation between VO and delta R by R is linear, and the relation between delta R by R and mechanical strain is linear, then ultimately the relation between VO and mechanical strain, that will be linear. But here, there is an hindrance. প্রথম স্টেপেই বাধা. The breach introduces a non-linearity. Alright. So what's the way out? The sensitivity in this case is 1 by 4. I have considered a normalized value of sensitivity. It's VO by VI divided by delta R by R. Because it's a ratio, it's dimensionless. It is 1 by 4. এইভাবে sensitivity consider করলাম কেন? I could have defined the sensitivity simply as VAB by delta R, isn't it? Then you couldn't have compared between different setups and different gauges. Because for different setups, VI would have been different. For different setups, the gauges would have been different. So if you try to consider the sensitivity, you should compare the sensitivity, you should consider a normalized form of sensitivity. For metal alloy gauges, see here that we may consider that delta R by 2R is very small compared to 1. So ultimately VO is proportional to delta R by R, so it's proportional to epsilon because gauge factor it will be constant. But for semiconductor gauges you cannot ignore delta R by R. You cannot ignore it, isn't it? So that is one part of the story. The breach introduces the non-linearity. Second part of the story is that the relation between delta R by R and epsilon, that itself is non-linear. That further adds to the non-linearity. So the situation is complicated. Now here, I have devised a single active gauge based bridge here. This is called 5-terminal quarter bridge with linearization. I have used an op-amp based circuit. Here if you analyze this circuit, you will get an output voltage VO which is proportional to delta R by R. No assumption has to be made. Irrespective of whether you are using metal alloy gauge or semiconductor strain gauge, it's proportional to delta R by R. So one part of the problem is removed. The bridge doesn't introduce any non-linearity. Another part of story is that now delta R by R versus epsilon in semiconductor gauges, it will be non-linear. There is no way out to compensate that. Alright, you have to go for certain other methods. So here I have considered two gauges, one under tension, one under compression. They are placed in the adjacent arms. Alright, why are they placed in the adjacent arms? They are identical gauges. One is under tension, one is under compression. We have placed it in the adjacent arms so that the temperature dependence of these gauges, the effect of the temperature dependence of these gauge resistances, that is cancelled out. Again, here the lead resistances will be there. Because of the presence of the lead resistance, the bridge balance equation will be such. Just have a look at this equation. VO equal to VI, RG1 plus RGL, etc. Presence of the lead resistance will not allow perfect temperature compensation. If the lead resistances are ignorable, then we may ignore them, and here just see 1 plus alpha E into delta T. This has to do with the temperature dependence of the gauges. That term in the numerator and denominator cancels out. So there is perfect temperature compensation. What happens to the sensitivity, normalized sensitivity? It is half. In case of the earlier single active gauge, it was 1 by 4. Now it is half. The sensitivity has doubled. Temperature compensation is there. Sensitivity is doubled. The last arrangement uses 4 active gauges. 2 under compression, 2 under tension. So here, just see. All the gauges, now because they are all placed in the cantilever of the structure, then what is happening? The Wheatstone bridge is formed locally. এই যে স্টেন গেটগুলো রয়েছে ক্যান্টিলিভারের উপরে, এগুলোকে কানেক্ট করে একটা উইটস্টোন ব্রিজ ফর্ম করা। The formation of the Wheatstone bridge, it takes place locally. So the connecting, here also you have to take a 4-core cable from the site to the control room, alright. But the lead resistances, the core resistances, they do not enter into the bridge arm. They are either in the supply branch or they are in the output branch. So they have no effect on the performance of the bridge, alright. Here if you analyze the circuit, no lead resistance business is here because they are outside the bridge arms and there is therefore perfect temperature compensation and sensitivity value, just see it's coming out as 1. So it is 4 times that of single active gauge. But problem is that, you may say that well, we will always opt for this configuration. Problem is that for any given structure, it's not always possible to mount gauges such that 2 are under identical tension and 2 are under identical compression. It's not possible to do that. Alright, that is the problem. That's why we have to go for other bridge configurations that I have discussed earlier. Now, you have, I'll just move on to diaphragm pressure gauge. Diaphragms, you cannot pressure gauge with simply strain gauges. There has to be some elastic element. One such elastic element was bellows, another elastic element is diaphragm. It is made of, again, stainless steel, brass, or beryllium, copper, or phosphor bronze, and it is very frequently made of silicon, so that it can be formed into microsensors. You have heard about MEMS, micro electromechanical systems. There silicon diaphragms are introduced. Now, there can be 3 types of pressure measurement. One is measurement of absolute pressure, where one side of the diaphragm is maintained at vacuum pressure, about 10 to the power minus 4 to 10 to the power minus 3 torr. 1 torr means 1 millimeter of mercury. So one side of the diaphragm is hermetically sealed, it's evacuated and hermetically sealed. So that is maintained at 10 to the power minus 3 to 10 to the power minus 4 millimeter of mercury. Other side is exposed to the pressure that you want to measure. This is one possibility. Second possibility is what is known as differential pressure. One side of the diaphragm is at some pressure, another side is at some other pressure. You want to find out the difference between the two. Depending on which side pressure is greater, the flexing of the diaphragm will take place accordingly. Whether it will bulge downward or whether it will inflate up in the form of a soap bubble, that will depend on the pressure gradient, pressure differential. Another type of pressure measurement is that one side is exposed to the ambient pressure, another side is exposed to the pressure that you want to measure. So this is also a gauge pressure, but here one side is at ambient temperature, that is fixed. Now, I have given typical dimension of silicon diaphragms used in these microsensors. 1000 micrometer into 1000 micrometer into 20 micrometer thickness. Alright. Now, I have shown here a piezo resistance based pressure gauge. Alright. The diaphragms that I am talking about, they are usually in the form of discs, very thin discs, the diaphragms, or they can also be in the form of a square. What is not very conspicuously visible on the surface of this square diaphragm, on the 4 sides, center of the 4 sides, 4 gauges are placed. I am calling them piezoresistive gauges because they are nothing but semiconductor strain gauges. So that's why they are called piezoresistors. The fact that the resistivity changes due to mechanical strain, that phenomenon is known as that is called piezoresistive effect. Alright. So here, under the action of the pressure differential, the diaphragm will flex. Because the diaphragm flexes, 2 of the strain gauges will be under tension, 2 will be under compression. You can configure a Wheatstone bridge here, and the output voltage may be calibrated in terms of that pressure differential that has occurred here. I have given you some idea about the areas where this is used. It is placed at the tip of a guard wire in balloon angioplasty to monitor the blood pressure. In automotive, the pressure monitoring, tire pressure monitoring is there, and in industrial environment, monitoring pressure in pipelines and tanks. Not only that, in automobiles, nowadays the cars come equipped with airbags, isn't it? Airbags are there. In the event of a collision with something, there is certain sensor that triggers the inflation of the airbag. The airbags inflate and protect the drivers and the other passengers by imparting a cushioning effect. So there some pressure monitoring is required. In that case also, these piezoresistive elements, pressure gauges will be used. I have given you some idea about the view of two pressure gauges. See here, there is a pad of fluorosilicon gel. That pad is there just for the protection of the surface and wear bond from harsh environment, nothing else. So this is a realistic view of the actual view of the diaphragm. Is the small thing that you can see here, very small thing. Either it is hermetically sealed on one side, or depending on, or it is exposed to the pressure, depending on what type of gauge is being formed. One use of this piezoresistive pressure sensor, or it can also be capacitive pressure sensor, is in spirometers that are used for lung function test. Alright, you can see here the view. Now come to NTC thermistors. Regarding the temperature sensors, in your school you have studied about platinum resistance thermometer probably. I have not considered platinum resistance thermometer because of that fact. Here I am considering thermistors, which are acronyms for thermally sensitive resistors. They are semiconductor components, semiconductor devices. They are made of sintered ceramics. Alright. Sinter means to pass from liquefaction to solidification. Alright. Without passing through the gaseous state, the sintering is done. Made of oxides of different metals, cobalt, nickel, etc. They have negative temperature coefficient of resistance. That means with increased temperature, the resistance values decrease. Alright. You can see here they are available in miniaturist form. Very small size. 0.25 to 1.5 millimeter. These are the peaks. They are also available as wafers. 0.25 to 0.8 millimeter thick. Problem is that they are inexpensive. Because of their small size, they have fast thermal resistance. What is meant by fast thermal resistance? These thermistors will be exposed to the temperature that you want to measure, isn't it? So suppose if there is a step change in the temperature, sudden change in the temperature sensor in general, its resistance will not change abruptly. But in case of thermistors, the resistance will not change abruptly, but it will not be, the change in the resistance will not be very slow. Almost instantaneous change. Almost. Because of their small size. Their sensitivity is very high. I have shown the resistance temperature characteristic. Sensitivity is very high. But the resistance temperature characteristic, again, it is non-linear. It is non-linear. Alright. That is the problem. So thermistor, it is used in several places. In all your domestic appliances, in refrigerators, in washing machines, in microwave ovens, etc. Everywhere. Because of their small size, cheapness, inexpensive, etc. Alright. Now, how would you place the thermistor in an appropriate electrical or electronic circuit so as to measure the temperature? Because resistance is not that you will take a multimeter and measure the change in resistance and from that you will measure the temperature. It's not like that. The temperature is varying with time. At the output, you want to have a signal that will vary with time in the same manner. So how to do that? I have given some examples where these thermistors are used. The nonlinearity is a problem. I have considered here, just see, the thermistor is placed from a constant current source, and the voltage across the thermistor through an instrumentation amplifier is taken to an analog to digital converter. Alright, analog to digital converter. Now here, just see, the constant current source feeds the thermistor, so the voltage VO, it will be I reference into RT. So VO is a function of temperature T. First of all, how will you devise a constant current source? The simplest way for devising a constant current source is to have a constant voltage source, a regulated source, stabilized source. You can have a stabilized source from Zener diode. That's what I have shown in the bottom figure. So the Zener diode supplies the thermistor through a high resistance. If this high resistance R high is very large compared to the maximum resistance of the thermistor, then what can you say? The voltage, the current that is flowing through the thermistor, it is Vz by R high. Approximately, it's a constant current. Alright. So VO is taken to the ADC, and the Zener voltage, it is used as the reference voltage of the ADC. So here what happens, the output of the ADC, which is a binary word and represents the decimal fraction, it is VO by V reference, I reference RT by V reference, ultimately comes out as RT by R high. So in the expression for the digital output, Vz does not appear. So even if there is a change in Vz, what may be the reasons for changing the value of Vz? It is temperature dependent. Alright, it will change with changing temperature. But we have made the circuit independent of Vz. So that's a betterment. Alright. But how from this digital output, which represents this decimal fraction RT by R high, how can you calculate the temperature? How? It is taken to some processor-based system. Can be a microcontroller, can be 2PC, can be FPGA, anything. Alright. So what the processor will do, from the measured value of FM, the processor will calculate RT. How the processor will calculate RT? Simply FM into R high will give you RT. R high is a fixed resistance. The processor stores it in its program or memory location. Now, the relation between temperature and resistance of thermistor, there are a highly accurate relation. The relation between T and RT that we have shown here, this relation is called Steinhardt-Hart equation. Now, if you calibrate the system, that means if you carry out measurements at 3 different temperatures, the lower limit, the upper limit of the temperature range of interest, and the midpoint of temperature range of interest, then from the measured value of resistances at these 3 temperatures, solving 3 equations, you can get A, B and C. If that is done, and if the temperature range of interest doesn't exceed 100 degrees centigrade, then it is found that a remarkable curve fit accuracy of 0.045 degrees centigrade is achieved. Just try to understand. With the thermistor, that is a highly nonlinear RT versus T, how accurate temperature calculation is possible. That the processor will take care of that. You need not interfere. I will consider diode temperature sensor. Alright. These are very important temperature sensor. What's the principle involved? A current I is being injected into the diode. The relation between I and VO, the current I and the voltage VO. I am claiming that voltage VO is temperature dependent. The relation between I and VO, it is given by the Stokes equation. I equal to Is e to the power Q VO by KT VO minus VGO. What are these parameters? Is is the reverse saturation current of the diode. Q is the magnitude of electronic charge. K is Boltzmann constant. And VGO is the band gap voltage. What does band gap stand for? For those who are in first year, you may have studied it in your school physics course. It's the energy difference in electron volts between top of the valence band and bottom of the conduction band. So here, from this relation, if you just maneuver it algebraically, you will find that VO will come out as KT by Q natural logarithm of I by Is plus VGO. So what does it appear to you? That the relation between VO and T, it is linear. For a given current ratio I by Is, if you fix this current ratio I by Is, isn't the relation between VO and temperature linear? So by measuring VO, you can have a measure of the temperature. And interestingly, apparently, the VO will increase with increase in this temperature. Alright. But one thing we have not thought about. What is this important thing? The important thing is that the reverse saturation current IS, it is strongly dependent on temperature. আমাদের তো মনে হচ্ছিল যে ভিওর সঙ্গে টি বাড়লে ভিও বাড়বে, ভিও will increase with increasing T, isn't it? কিন্তু because IS is strongly dependent on temperature, the relation is just the reverse. With increasing T, VO will decrease. I am showing you the characteristic. This is the characteristic shown by the curve. Alright, this is the characteristic. I have drawn the maximum slope straight line and the curved characteristic. Here what I have shown, truly speaking, instead of a diode, a transistor is preferred. Transistor in the diode mode, because that will allow for larger values of IC by IS. Diode ক্ষেত্রে I by IS এর যত maximum value use করতে পারতাম, এখানে IC by IS এর অনেক বেশি value use করতে পারবো. The temperature dependence is less in case of transistors. Alright. So here the base to emitter voltage, just see here, it has a relation of apparently linear relation with T, but in practice, because this J is the current density, the reverse saturation current density, it's dependent on T, it's T to the power n. Actually VBE, the base to emitter voltage, it decreases with increasing T. But we desire that the relation between VBE, some voltage and temperature should be linear, and it should also increase with increasing the temperature. What's the way out? Here is the way out. I have considered two transistors. You can see Q1 and Q2. What are the nature of these transistors? They are identical in all respects, with the exception that the emitter area of Q1 is n times the emitter area of Q2. Alright. That is the exception. The same current is injected through both of the transistors. So here we have two base to emitter voltage. One is VBE1 for transistor 1, another is VBE2 for transistor 2. VBE1, according to the expression that we have derived, it is IC into NAJS. Here in case of VBE2, you have IC divided by AJS. This is the difference. This N factor is here. Now if you subtract VBE1 from VBE2, delta VBE, this is the voltage delta VBE. If you subtract delta VBE2 from VBE1, just see here, the term J's cancels out. If the transistors are perfectly matched, with the exception that the emitter area is of Q1 is n times the emitter area of Q2, then we can have the J term cancelling out. N is a constant, K is a constant, Q is a constant, so delta VD is proportional to T. So this type of sensor is called proportional to absolute temperature sensor. PTAT is the abbreviation. Proportional to absolute temperature. Now this type of sensor is used. It can be a single transistor or it can be this PTAT sensor that is used in several cases. Cold junction compensation of thermocouples, that is one application. Another application is that monitoring and overheating of chips. This is very, very important. It can be the PTAT sensor or simply a single transistor, complement to absolute temperature sensor. Where is it used? Have you found any use of this type of sensor? You all use laptops, you all use mobile phones. Wherever you have a CPU, the processor, this type of so-called thermal diode monitor is inbuilt into the CPU. এই ধরনের সেন্সর সিপিইউ গুলোতে ইনভাইট করে দেওয়া হয়, এমবেড করে দেওয়া হয়। এমন নয় যে আলাদা করে এই ট্রানজিস্টর এই ডায়োড কিনে এনে বসানো হচ্ছে, তা না। When the processor is being fabricated, in the fabrication process, this transistor or diode monitors, they are inbuilt into the die. Alright, so that is the importance of this type of sensors. I have shown here for older variety of processors, as for example Intel Core Duo processor, there was one on-chip thermal diode monitor with analog output and several thermal diode monitors distributed on the die close to all hotspots. In modern processors, there are multitude of such sensors, and where the sensors will be located on the die, where are the probable hotspots, finding out those spots, that is itself a topic of research. Alright, a topic of research. So this is the importance of this type of sensors. Come to capacitive sensors. Probably this will be the last type of sensors that I'll cover. What's the principle involved? The physical variable that you want to measure, it brings about a change in the capacitance. How can it bring about a change in the capacitance? Either by changing the separation between the electrodes, or by changing the overlapping area of the electrodes, or by changing the permittivity of a portion of the complete dielectric. So there are physical variables, different types of physical variables that can be measured. This is simplest variable air gap position transducer. Alright, variable air gap. Lower electrode is fixed in position, upper electrode is coupled to the object in motion. It moves either up or down, towards the fixed plate or away from the fixed plate. Here we want the change in the capacitance delta C, it should be proportional to delta D, or linearly related to the displacement delta D. But that is not happening. In this case, the change in the capacitance from the nominal value, it is not proportional to delta D. That 1 minus delta D term comes in. But here, if the displacement delta D by D, the normalized displacement, the fractional displacement, if you are only interested in displacement that are very small, then delta D by D can be ignored in comparison with 1. So the relation between delta C and delta D, it becomes linear for practical purposes. Now, coming to this type of sensors, there was a particular reason why I considered capacitive sensors, because they are very important variety of sensors, no doubt. But because you are students of first year and second year of engineering, you must, just 1 minute. Try to understand one aspect related to capacitance that will be useful not only for sensors but for other applications. See here the expression for capacitance that I have considered. That expression I have not taken into account one fact. What is that fact? One aspect. I have ignored the fringing effect of the electric field lines here. This capacitive sensor, it will be placed in some electrical or electronic circuit. So, there will be a potential difference between the two electrodes, isn't it? That means an electric field will be there, electric field lines. At the edges of the electrodes, the electric field lines will bulge outward. That will make the relation between delta C and delta D more nonlinear. So how to at least get rid of this fringing effect? How to do that? Students, do you have any idea? We use a so-called guard electrode. Just see here, this was the situation. When it is placed in some electric circuit, the lines bulge out. Now I have encircled, I have encompassed one of the electrodes or the sensing electrodes by a guard electrode. Alright, encircled it by a guard electrode. These three electrode capacitance, when it is placed in a circuit such that the sensing electrode and the guard electrode, they are almost at same potential, then apparently the combination of the two, they will serve as a single electrode, combination of the two. So there will not be bulging out of the electric field lines. The earlier bulging out of the electric field lines between the sensing electrode, two sensing electrodes will not happen here. But the bulging will take place at the exterior. I mean, at the ends of this guard electrode. And guard electrode doesn't come into this circuit. It's so arranged. So the electric field lines in the middle, they are parallel. Thus you get rid of the fringing effect. Alright. And you get rid of one source of nonlinearity between delta C and delta D. This is the top view. This is the top view. The separation between the guard electrode and the central electrode, it should be infinitesimally small. But in practice, it cannot be infinitesimally small. It will be small but finite. So there are certain empirical rules using which you may decide what will be the separation. Alright. I will skip this one. Now here I have shown some examples of application of capacitive sensors. First one, the top left one, there what is happening? We are sensing the flatness of the surface. We are having a metal surface whose surface is not flat, and we have brought in the so-called capacitive probe close to this. So the capacitance, if the metal surface were flat, the capacitance would have been constant between the two. Alright, if you move it, it would have been constant. Now, if it is not flat, when you are moving it, the capacitance between the two, it will change. So if you place these two electrodes, the electrodes of the capacitor in an appropriate circuit, by measuring the output of the circuit, you can have measuring the pattern of variation of the output of the circuit, you can have a check for the flatness. On the top right figure, a strip is vibrating, metal strip is vibrating. And from the right hand side, this is the probe. So the capacitance is continually changing. We have placed it in an AC circuit, and the output of the AC circuit, you can see the amplitude of the output is continually changing. So from the peak to peak value of this output, the pattern of variation, you can have a measure of the extent of vibration. In the bottom figure, in the there are two probes. Now we are trying to find out the tilt sensing, whether there is a tilt in this metal surface. So we have placed two electrodes. Alright. One probe to metal surface, this capacitance is C1, another probe to metal surface, this capacitance is C2. So, by comparing C1 and C2, you will be able to understand whether there is a tilt. Who will compare? You will not get a capacitance meter and measure and then compare. It's not like that. But some automated arrangement has to be there. One possible circuit is that this is one possible circuit. Two voltage sources, 180 degree out of phase, and C1 and C2, these are the capacitances. That's how they are connected. Just see in case of C2, I have considered a guard ring, and the sensing electrode is connected to virtual ground, the guard electrode is connected to actual ground. So the potential difference between guard electrode and the central electrode is almost same. The potentials are almost same. Now here, you may say, well, sir, how will we get two voltage sources whose voltages are 180 degree out of phase? It's very simple to get. You get a single voltage source, then use an inverter circuit. Op-amp based circuit, inverting amplifier, both resistances are equal. Feed forward and feedback resistances are equal. You get another voltage source, another voltage, whose voltage is 180 degree out of phase with the source. So using this thing, ultimately you get an output voltage EO. The expression for EO is delta C by CF ds. Alright. So the output voltage, it's a measure of delta C, the difference in the capacitance between the two. This difference in the capacitance, it may change with time. Because the tilt may change with time. It will depend on so many things. The temperature, the applied stress, etc. So delta C may change with time. But ultimately you should have some output voltage which should be changing with time in the same manner as delta C is changing. So ultimately you should have some signal that is proportional to delta C as a function of time. Alright. So here we have used the so-called synchronous demodulator. For those who are interested, I have introduced this circuit. The signal EO is multiplied with the external excitation voltage Vs itself. So the product comes out as ET. The output of this multiplier, it comes out as one term is proportional to delta C, another term is delta C into cos twice omega CT. You can see a low pass filter, the second term is filtered out. So you get E as a function of delta C. This type of synchronous demodulation circuit, for those who will be studying ECE, these are widely used. Synchronous demodulation or coherent demodulation in communication systems, widely used. Now I am considering an astable multivibrator circuit. Astable multivibrator circuit. Why have I considered an astable multivibrator circuit? For the sake of simplicity, I have considered a 555 timer based circuit. So the output is a pulse train. Alright. RA and RB are the two timing resistances. The sensor is used as the timing capacitor. The sensor capacitance, I am considering the variable air gap sensor. The relation between delta C and delta T was not linear, remember. Here I am trying to make it linear. Cx, its expression is epsilon naught A by D minus delta D. From the expressions for T, T8, Tb, T1, T2, you can derive an expression for F, which is 1.45 by Ra plus 2Rb into Cx. Replace Cx with epsilon naught A divided by D minus delta D. Alright, you get this expression, which is some constant frequency F0 minus delta X. F0 is the frequency when delta C is 0, that is called nominal frequency, and delta F is the deviation of the frequency from this nominal frequency. Just see that the relation between delta F and delta D, it is linear. So it has linearized. We have obtained a circuit, an arrangement where the output has a linear relation with the input. What other advantage is there in case of astable multivibrator circuit? First of all, the output of the astable multivibrator circuit is quasi-digital, semi-digital. You don't require any ADC. If you want to take it to a processor-based system, you don't require any ADC. You can take it in to a processor-based system. Another advantage is that, see, the output is a pulse stream. Alright? So what will happen? You can communicate it over a large distance. If you communicate this output pulse stream over a large distance, the pulse shapes will get distorted. There is no doubt. The amplitudes will decrease. There is no doubt. But what will remain unchanged? The time period and the frequency of the pulse stream. That will remain unchanged. And the frequency or time period bears the useful information. So at the other end, you may use a sweep trigger to rejuvenate the exact rectangular pulse stream, and by measuring the deviation in frequency from the nominal value, you can have a measure of. You means you will not take a meter and measure. The processor will take care of that. Alright. I have considered here a touch sensor. Just see the type of sensor that you use in touch screens. Here there is a copper pad and there are plexiglass substrate is there, PCB is there, alright, at the top there is a glass cover. In between the copper pad and ground there will be some capacitance CP, the parasitic capacitance. If you bring in your finger and place it on this plexiglass, or window glass or plexiglass, what will happen? Another capacitance will be formed through your finger to ground. So this capacitance will come in parallel with that capacitance CP. So there is an increase in the capacitance. If you take connections to some type of signal conditioning circuit, this increase in the capacitance will increase the output voltage or increase the time period of the pulse stream, etc. So this is the principle involved. Liquid level gauge, two metal plates are inserted. This is the liquid level gauge for non-conducting liquids. Two metal plates are inserted, and when the entire space is air, then the capacitance say is C0, and now the liquid has risen, alright, along this path. So the liquid level is delta L. Now delta C is proportional to delta L. So it's linear relation, fine. What will happen if I try to measure a conducting liquid level? What will be the arrangement? Can capacitive sensor be used? Arrangement is simple. A cylindrical rod is there. That cylindrical rod is encircled by a solid insulation, and that is immersed in the conducting liquid. So what is the arrangement? I have shown the top view, right bottom figure. So black one is the conducting cylinder, metal cylinder. Then yellow one is the encircling insulation, the wrap of insulation. Surrounding it is the liquid, can be tap water. So this arrangement acts as two coaxial cylindrical electrodes. One electrode, the inner electrode is the metal rod, the outer electrode is that water. So the outer electrode height, that is changing with time. So by measuring this capacitance, what is happening here? The outer electrode height is changing with time. So here by measuring this change in capacitance, you can have a conducting liquid level gauge. This type of arrangement, we in our lab, the undergraduate students perform an experiment. As we were frantically searching from some setup for measurement of levels for conducting liquids, there are a lot of such gauges available, but they all come in ready-made form. The signal conditioning circuit is there, the microprocessor is there, complete thing. But we don't prefer that type of circuit. We want to expose our students to circuits right from the scratch. So what was the way out? Suddenly it occurred to us that you have the drums of the computer printers. The drums of the computer printers, the rollers, they have a metallic cylinder with a wrapping of insulation. So we use that as the level sensor, and the experiment is running very smooth. The relation between delta C and delta L is almost linear, but due to some imperfections in the insulation, it's not exactly linear but almost linear. All right. And we are performing experiments with tap water. We have a capacitive humidity sensor. Some dielectrics have the property of আমার কি বেশি হয়ে যাচ্ছে
না স্যার ঠিক আছে
আর বেশি নেই 5 slides or 6
ঠিক আছে স্যার
now there are certain dielectrics that have the capability of absorbing moisture from the air. Their permittivity increase with increase in the relative humidity, because moisture content of air it is related to the humidity. So those dielectrics whose permittivity when they absorb moisture from the environment change repeatably, alright, reproducibly, those type of dielectrics are used. Alumina is used, and there are certain special purpose polymers. We call them proprietary polymers. What does the adjective proprietary mean here? Special purpose polymers whose exact composition the manufacturers they won't divulge. So that type of polymer is used, and these capacitive humidity sensors that are widely used. I have given you this home weather station hygrometers, automatic windscreen wipers, medical device, humidity controllers, etc. So because of the increase in humidity, increase in the permittivity with increase in humidity, what happens? The capacitance value changes. So if you place it in some signal conditioning circuit, can be the multivibrator, alright, you will get an output which will be directly related to the humidity. These are some view of practical relative humidity sensor. You can see the vents through which moisture pass into the dielectric. Alright, pass into the dielectric. Lastly, you have the accelerometers. In the heart of all accelerometers that we consider, we have a seismic accelerometer. It's a spring mass damper system. The housing is rigidly mounted onto the workpiece whose acceleration we want to measure. In the inside, you have a spring mass damper system. Intentional damping is usually not provided, or whenever it's provided, it is implemented using that silicone oil. Alright, for a well-designed accelerometer, here the acceleration that we are interested in is the second derivative of Zi. Now because of this acceleration, what will happen? There will be a relative motion between the seismic mass and the base of the casing. That motion is ZO. For a properly designed accelerometer, ZOT is proportional to AT. So by measuring ZO, we can have a measure of the acceleration. How to measure ZO, the displacement? There are several displacement transducers. I have discussed some of them. You can use a resistive potentiometer. You can use a capacitive sensor. If you know about LVDT, LVDT can be used. You can use piezoelectric sensors to consider to measure this displacement, and consequently, here there are examples of capacitive accelerometers. Spring mass system is there, and on the base there is a static plate. Here the acceleration is in the vertical direction. So the moving mass, the proof mass, it serves as one of the electrodes, the moving electrode of a capacitor, and the base fixed electrode is this static plate. So due to acceleration, the seismic mass moves either towards or away. There is a change in capacitance. Here the moving mass, it's through a cantilever, it is attached to the wall of this housing. So here also, as the accelerometer accelerates, what happens? There is a displacement of the moving plate in this way. The curvature is not much. I have shown an exaggerated view. If you are interested in horizontal displacement, you can place it in this way. Static plate is here, moving plate is there. Alright. Don't think that this moving mass, it is hanging in air. They are provided with mechanical guides, which I have not shown in this figure. Alright. Here there is an example of an accelerometer where you are using piezoresistive sensors. Seismic mass is of silicon. This is used in MEMS devices. Alright. Silicon seismic mass. This is also of silicon, and these appendages, these projections, they represent the springs. So if there is a deflection of the seismic mass towards the base or away from the base, what will happen? Of these four strain gauges, two will be under tension, two will be under compression. You configure these gauges, alright, take the output voltage, it will be calibrated in terms of acceleration. This type of accelerometer, it can be a capacitive accelerometer, it can be a, what should I say, piezoresistive accelerometer. They are used in mobile phones. You know the use, isn't it? You already know the use, why they are used. If you just, with the change in posture, with the change in position of the hand, you can do several things. Those are taken care of by the accelerometers. In the earlier laptops that used hard disk drives, that did not use solid state drives, they were provided with accelerometers so that when it is working, if there is a fault from your hand, the accelerometer would send out a signal and that read-write head would move away from the hard disk platter and park it in some static position, safe position. Nowadays solid state drives are there, so it is not really used, I think. This is that airbags used in moving vehicles, in automobiles, to protect against accidents. What happens whenever there is a collision with the of the car with something? Alright, the capacitive or piezoresistive accelerometer, it senses the vibration. It sends out a signal to the control unit. The control unit sends out a signal to the igniter. There is an igniter, and there is a compound called sodium azide, and probably together with its potassium nitrate is also present. So those compounds are ignited, they vaporize and they generate nitrogen. Nitrogen inflates these cushions, these airbags, so as to protect the driver, to protect the passengers. So accelerometer does all these things. And there are also pressure sensors, piezoelectric pressure sensors, etc. Because pressure also has to be monitored. Because once the bags have got inflated, after that they have to be deflated. So the pressure has to be monitored. Alright. So this is more or less what I wanted to say. I'll just add up just one more point. Students may have question about gyroscopes. Alright, gyroscopes. Alright.
Sir, you may continue.
Do you have interest about the gyroscopes used in mobiles? The gyroscopes, they make use of a certain phenomenon that is known as Coriolis effect. You try to go through that textbook, Coriolis effect. What is that? A vibrating piece is there in between two frames. When the mobile rotates, that frames rotate, but that element is continuously vibrating. Alright. Due to this Coriolis effect, there is a force on that element perpendicular to the direction of vibration. So that displacement, there is a displacement. That displacement is sensed by some capacitive sensor or by piezoelectric sensor, and the necessary signal is sent out. So that is what I wanted to say. Thank you very much.
Thank you so much for the informative session. Now I would like to request the audience, if anyone is having any question, the question answer forum is open. So you can just ask the question, sir is here. And the session was so informative and detailed discussion about the sensor, electrical, electronics. I think students here, please carry forward and please focus and tell some questions to make yourself explore with the topic. Any questions?
আমি চেষ্টা করেছি যতটা সিম্পল রাখা যায়। তোমরা যেহেতু ফার্স্ট ইয়ার সেকেন্ড ইয়ারের স্টুডেন্ট,
Okay, so any question from the audience section? Then we can conclude with the first session of the today's seminar, and we are carry forward our seminar to the next session.
হ্যাঁ স্যার এটা এন্ড করে দাও ম্যাডাম ম্যাডাম আমি এন্ড করে
Thank you so much, Dr. Munshi sir, for your expert
Link
talk
and
in the
code
electrical sensor domain. Now we are moving forward to the next part of our one-day seminar, and it is my honor to be here to introduce and welcome Dr. Sivaji Chakravorty sir to share sir's expert talk in soft skill development in engineering profession. But first of all, I would like to give a brief introduction.
W HW ZQ হ্যাঁ হ্যাঁ আমি ওটা করে দিচ্ছি আপনি ওটা আমাকে জয়েন করা admit all first one
No, stop.
Class.
Okay, so we are moving to the second part of the today's one day seminar, and it is my honor and privilege to have Dr. Sivaji Chakravorty sir for the second half of the session, and sir is going to share sir's expert talk in cultivating essential soft skills to thrive in a world of constant change. But before that,
Stop. Hey students, now I start with two assumptions or two things. Assumption number one, ये दो बुद्धा आए हैं. Do you want to really hear us? The answer is no. Nobody wants to hear all those Buddhas. क्या बता रहा है ये सब, ये पहले जो हो रहा था, क्या सुनते थे? আমি যদি তোমাদের জায়গায় থাকতাম আমিও শুনতাম। আর দ্বিতীয় একটা গল্প বলি। It's an old story. Recently a movie came, Oppenheimer. How many of you have seen? Raise hand. Raise hand. How many of you have seen Oppenheimer? Oh, very few. I am disappointed. Oppenheimer. Today go back, it is available in Netflix. You just see, open Netflix and see. It's a very good movie. And in that movie, there is a character, Richard Feynman. How many of you have heard the name Richard Feynman? Again, I see only one hand. Anybody else? One hand there. Now, Richard Feynman is arguably one of the most brilliant physicists of the last century. Nobel Prize patient, got the Nobel Prize in physics. So when he was doing his PhD in Berkeley, of course one of the topmost university in US, you know, उनके पास एक rule था कि whatever they were doing, you have to present every 6 months or something. So his supervisor, guy, told, hey Richard, come. You have to make presentation on next Wednesday. Yeah, fine. Then on Monday, his supervisor again called, hey Richard, come. I just got the information that Professor Einstein is coming for your lecture. And he started trembling. I mean, what for Professor Einstein is coming to my presentation? And his supervisor saw that Richard is trembling. He said, "Are you डर गया क्या?" Of course. अरे भाई डरो मत. Do you know why Professor Einstein comes for these lectures? No, sir. He comes here for sleeping. Because that's the only 1 hour nobody disturbs him. So you got my point, right? So you can do that. Right? And the third question, now my first question, what time you have to catch your bus to go home? Because I am told at 5 or something, 5:20. So I have to finish by 5:10, not later than 5:10. Then my soft skill is very bad. Right? So because it's also a test of my soft skill. And today's world, when you will be working after passing, don't think your success will depend on what you know, etc., etc. It will depend on your soft skill also. And what is that? Nobody knows. You only learn by hard experience. Hey, when somebody change the slide, I am not going there. I will bombard the students from here. Okay. See, this sort of talks is called motivational talk. तो एक बुद्धा है मोटिवेशन के लिए, एक बार क्लिक करो और एक बार सी, ये हमारे जैसा है ना, देखो व्हाइट हेयर, कितना अच्छा लग रहा है ना, बहुत बढ़िया, एकदम hall full of people, everybody is listening just like you. और एक बार क्लिक करो, अभी थोड़ा सामने जाके देखते हैं कैसे क्या हो रहा है, और एक बार क्लिक करो, क्या हो रहा है, तो आइंस्टाइन है ना, इसीलिए आए हैं लेक्चर के लिए. And now I am that person on that side, and it is my soft skill, so that at least you listen something what I am saying, because then I am successful. Otherwise, I am a failure. Okay, आगे बढ़ो. This is the one I like to show you. Please see this. And this is not my card. These cards are taught in management courses. One of my friends is a management faculty in a very big institute. He gave me this one. And this is called Dunning-Kruger effect. X-axis is what? Knowledge. Y-axis? Confidence. So what you see in this card? When your knowledge is less, your confidence is very high. Damn confidence. Right? So I was like that. When my knowledge was not that much, I was damn confident. I used to say, अरे वो क्या जानता है? उसके बाद my knowledge increased, and as my knowledge increased, क्या हुआ? अरे भाई मेरा confidence गिरा. हम तो ज़्यादा जानते नहीं. तो इधर नॉलेज गिर गया. उसके बाद और नॉलेज बढ़ा. क्या हुआ? अभी थोड़ा कॉन्फिडेंस बढ़ा. अभी जब हमारा यार अभी पूरा वाइट हो गया. एक जमाने में हमारा भी काला था तुम्हारे जैसे. तो अभी थोड़ा कॉन्फिडेंस बढ़ा है, लेकिन जो पहले वाला कभी नहीं हुआ. वो जो पहले था ना, वो वाला कभी नहीं हुआ. और जो लोग तुम पढ़ाई करते हो ना, कुछ वो एनर्जी बैंड गैप ऐसा कुछ है ना, है ना? दिस इज कॉल्ड कॉन्फिडेंस बैंड गैप. यू कैन क्रॉस. तो ऐसे लोग भी मिलेगा तुम्हारे क्लास में मिलेगा, बाद में तुम्हारे जॉब करोगे वहां पे भी मिलेगा, सब जगह पाओगे. एक क्लास का जो मैनेजमेंट के प्रॉब्लम है, ওটা এই জন্য তোমাদের টাকা দাও. নেক্সট আগে বলো. First. You understand proverb? Proverb is so, it comes from long time back. Now India is a very old civilization. हमारे सभ्यता बहुत पुरानी है. जापानीज भी बहुत पुरानी है. This is a Japanese proverb. क्या लिखा है एक बार पढ़ो. Misinformed. If you think that you know everything, you must be misinformed. ऐसे लोग भी मिलेगा. तुम्हारे क्लास में मिलेगा, बाद में तुम्हारे जॉब में भी मिलेगा. मिला है? जरूर मिला है. आगे बढ़ो. इसके बाद फिर आइंस्टाइन के पास आ गया. ठीक है, हम whatever I am talking today हमारी बात नहीं है. वो सब ऊंचे लोगों के बोला है. एक बार आइंस्टाइन was asked, then he said this thing. He said कि दुनिया में दो ही चीज है जो इनफाइनाइट है. एक तो हमारा यूनिवर्स है और दूसरा कौन क्या है? पढ़ो. ह्यूमन स्टुपिडिटी. और उसके बाद आइंस्टाइन साहब ने बोला कि I am not sure about the universe. That means universe can be finite, but the other one is definitely not finite. ये भी तुमको देखने में मिलेगा. आगे बढ़ो. ये देखो, इसमें तुम लोग इसको मीम बोलते हो ना. मीम बोलते हो ना. अरे भाई हम 6 महीने पहले इसको मेमे बोलते थे. और हमारे डॉटर ने इतना राना मेरे को कि यार ये बुट्टा तो जानता नहीं है कि इसको मीम बोलते हैं. ये अभी इसको मेमे बोल रहा है. तो ये देखो, ये सोच रहा है कि अरे हमको तो बैटमैन है. But that fellow is not Batman. He's just a dog. ऐसे आदमी भी मिलेगा. इधर देखो, लेफ्ट एंड राइट मिलेगा. आगे बढ़ो. तो इसीलिए जो सॉफ्ट स्किल्स में आजकल तो सभी बोलते हैं ना, एवरीबॉडी टॉक्स यू शुड हैव गुड सॉफ्ट स्किल्स। इंटरव्यू में भी वही बात होता है, जॉब के इंटरव्यू में क्या है सॉफ्ट स्किल्स? दीज आर नॉट टेक्निकल स्किल्स। जो ये बुद्धा वाला है वो भी नहीं है, हम जो पढ़ाते हैं वो भी नहीं है। So these are something which are some of your your personal characteristics है। But important thing that what I want to hit upon you is that you have to develop it. इसको लेके हमारा जन्म नहीं होता है। You have to develop it. That's the important part. आगे बढ़ो। Okay, now everybody talks about communication. The communication जो भी हम whenever I say, I find everybody says, वो अंग्रेजी बोलना ही communication है। फटाफट अंग्रेजी बोल लेते हैं, मतलब communication में बहुत बढ़िया है। ठीक नहीं है। That's not communication. Only maybe 30% of the communication. I will give you something. आगे बढ़ो। Now language, एक question है हमारा। Is it a barrier? क्या है तुम्हारा ओपिनियन? बैरियर तुम समझते हो? लैंग्वेज ये क्या बैरियर है क्या? है ना? हाँ। अच्छा अभी किसी रूम में कितने सारे लैंग्वेज के आदमी हैं? बहुत सारे। ठीक है। अच्छा एक बात बताओ, तुम्हारा लैंग्वेज क्या है? बंगाली। तुम्हारा क्या है? पीछे बंगाली है। हिंदी कोई आए यहाँ पे? बहुत सारे हैं। अच्छा जब तुमने बंगाली सीखा था, तुमने हिंदी सीखा था, किताब पढ़ के सीखा था? कैसे सीखा था? हाँ हाँ बहुत बढ़िया। सुन दैट्स द इम्पोर्टेंट पॉइंट। एक चाइल्ड, अब तुम तो छोटे थे तभी सीखे थे ना, तो जो छोटे बच्चा सुनते हैं ना कान से, वही से सीखता है। तो जब अच्छा अंग्रेजी बोलना है तो क्या करना है? तो सुनना पड़ेगा, अच्छा इंग्लिश सुनना पड़ेगा। कैसे सुनोगे? कैसे सुनोगे बताओ? नहीं, वो मोबाइल से जो रील आता है ना 1 सेकंड का, उसमें नहीं होता है। मेरा सजेशन है, अरे मूवी देखो, 1.5 घंटा का मूवी देखो, वही जो चलेगा ना 1.5 घंटा, तो एट द फर्स्ट टाइम यू विल नॉट गेट एवरीथिंग। पहले जो है इट विल बी वेरी डिफिकल्ट, बट वॉच रेगुलरली। अभी तो क्या है, अमेज़न प्राइम है, नेटफ्लिक्स है। हमारे जमाने में कुछ नहीं था भाई, टीवी नहीं था, तो सुनना पड़ेगा। दैट्स द फर्स्ट थिंग, यू हैव टू लिसन। और एक दूसरा चीज करना पड़ेगा। Just do it, you will tell me that whatever I have told you. You have to read also. पढ़ना है। And that is not your textbook, or not वो क्या हुआ है, वो जो मोबाइल में आता है। At least one article, छोटा सा, ठीक है। Again, you will see at the very beginning it will be very difficult. जब हम जादवपुर यूनिवर्सिटी में ज्वाइन किया था, कब? बहुत दिन पहले, 1979। कितने साल हुआ? चलो 46 ईयर्स पहले। हाँ, मोबाइल था, इंटरनेट था, टीवी था, कुछ नहीं था। तो हमने रेडियो था, बहुत बढ़िया। तो मैंने एक बंगाली मीडियम स्कूल से पास किया था, जैसे तुम्हारे यहाँ का बहुत सारे स्टूडेंट हैं। और जादवपुर यूनिवर्सिटी में पहले दिन जो किया था, द फर्स्ट डे एवरीथिंग वाज इन इंग्लिश, and no teachers used to talk in Bengali, no teachers used to talk in Hindi, only in English. And then Jaadavpur University followed semester system, so basically it's a matter of 4 months. Semester is a matter of 4 months. So I have to survive, otherwise I am gone. So what to do? I have to learn. तो सीखना पड़ेगा. So then I did exactly that. And I said that time there was no TV, there was nothing. So वो movie देखना नहीं था हमारे. So I started reading. And what? Just one article. Newspaper में. And which one? Whatever I like. तुमको मूवी पसंद है, तुमको खेल पसंद है, इसको कुछ दूसरा चीजें पसंद है, तो one article. Again, the beginning, at the beginning it is difficult. But just keep on trying. After 3 months you will see the difference. Just try it. हाँ पहले सपना दो. और उसमें क्या होगा? यार छोड़ो इसको नहीं कर. You watch the movie. पहले क्या होता है? अरे कुछ समझ में नहीं आया क्या बोल रहा है? वो हीरो हीरोइन वगैरह क्या बोल रहा है? उससे तो अच्छा है बॉलीवुड का मूवी. Now you have to try. आगे बढ़ो.
छोड़ो आगे.
See, when we talk in particularly in the engineering field, अच्छा एक बात बताओ. Just tell me one thing. क्या बहुत बड़ा इंग्लिश चाहिए क्या? Big words, long sentences? Absolutely no, I tell you. Today I sit in many national and international meetings. And there are many senior people from very big companies come. Or at least half of them, if you hear their English, you will laugh. The people from Korea, people from Japan, people from China, people from Taiwan, these places. Their English is horrible. But they are CEOs of big companies. So what is the important point I have noted that they can't speak very big things, but they speak in short sentences and meaning is clear. समझ में आ जाता है क्या बोल रहा है. Can you do it? Yes, you can do it. But ये सोचना है, सीखना है, प्रैक्टिस करना है. प्रैक्टिस करोगे? नहीं भाई. दर्द होता है, सदर्द होता है ना. उससे तो अच्छा है बंगाली में बात करो, हिंदी में बात करो, दोस्त लोग हैं. That's the problem with us. That's the problem with us. That's why we don't learn. आगे बढ़ो. अच्छा एक और एक बात बताओ. कम्युनिकेशन की बात कर रहे थे ना. कम्युनिकेशन मतलब ये नहीं है कि सिर्फ अंग्रेजी बोल रहा है. अच्छा I have seen many people and I was like that at the very beginning. See, I wanted to say something. I prepared something. So when I came, I started speaking so fast, just complete everything before I talk. That's one way of talking. The other way of talking is, I'm not very sure, okay, so I say something, then think, again say something, so very, very slowly. ये दोनों ही गलत है. क्या what happens? When you speak very fast, you make mistake. Definitely you make mistake. And when you go very slowly, then the other people think that person is not confident. So this is a balance. That what speed you will talk, that matters. Now today when I am talking to you, don't think that I have learned it at the first place. I have learned it over years. तो ये बोला ना जब बाल काला था रवि बाल सफेद होते इतना दिन चला गया. उसके बाद ही ये सब समझ में आया. I am just sharing you with that. और जो बात जाके बोलोगे भाई क्या ध्यान दे रहा था ये बुद्धा आके. आगे बढ़ो. Just a couple of again very famous people what they say. बेंजामिन फ्रैंकलिन आप जानते हो? हाँ? आप जानते हो? क्या कौन था? पूरा नहीं जानते हो. बताओ कि यूएस प्रेसिडेंट था. फिर अमेरिकन प्रेसिडेंट था. बहुत दिन पहले. You see the time 1706 to 17 that time. Now what he said, just see one sentence. Just read. See, एक जो गाड़ी होता है ना, सबसे ज्यादा नॉइस कहाँ से आता है? From that wheel which is damaged. You get my point, or get his point. That the damaged thing always makes the most noise. Are you getting my point? एक मीटिंग में 10 आदमी बैठे हैं, एक आदमी नॉइस कर रहा है, इसका मतलब है ये. So that's also part of communication. Don't make noise. You will understand that this noise is coming from the damaged thing. और उसके बाद मार्क ट्वेन आप जानते हो? You know Mark Twain, anybody? Another great writer of course in English, American writer. Now he said what? Just read one small sentence. Read. Just read. Hey, आगे मत करो. It is better to keep your mouth closed. मतलब मुंह बंद रखो and let people think that you are a fool. मुंह बंद रखो, लोग को समझने दोगे तुम fool है. Then to open it and remove all doubt. Then you open your mouth और सब doubt चला गया सब. कौन सा doubt था? कि ये fool है कि नहीं? Now nobody has any doubt. So that's again stated by one of the very, very famous people. So talking is a very, very important topic. It's not only English. Are you getting my point? Okay, आगे बढ़ो. अच्छा, एक बात बताओ. Now we'll just tell you one thing. In English there are two terms. One is to see. Another is to observe. Are the same? Same or different? You are not sure? Different side? अच्छा, बहुत बढ़िया. अच्छा, एक टेस्ट लेते हैं. Let's take a test. हमारे देखो, हमारे पास और बताओ कि ये सीलिंग फैन कौन सी डायरेक्शन में रोटेट कर रहा है, क्लॉकवाइज और एंटी क्लॉकवाइज? यही ऊपर देख रहा है, क्लॉकवाइज. अभी देखो देखो देखो, ये क्लॉकवाइज घूम रहा है, तो क्लॉकवाइज बोल रहा था. अच्छा, तुम्हारे ऊपर तो 24 घंटा घूम रहा है. हाँ, अरे भाई एंटी क्लॉकवाइज ही घूम रहे हैं. देखो, तो तुम्हारे ऊपर 24 घंटा घूम रहा है. देखा क्यों नहीं? देखा है बट ऑब्जर्व नहीं किया. नाउ यू सी द डिफरेंस. एंड दिस इज ए सॉफ्ट स्किल. दिस इज ए ग्रेट सॉफ्ट स्किल. ऑब्जर्व करो, क्योंकि इस दुनिया में, इस this world, everything will not be told to you. कि सब आके बोल देगा कि भाई ऐसा करो ऐसा करो. You have to observe and perform. This is the mantra. Next. In English there are two words. To hear, to listen. Same है. Listen and hear. Again different. One is just, going through ears. That is hearing. Another is listening. I give you an example. सोचो कि ये दोनों दोस्त है. You just tell me whether I am wrong. हाँ? सच में दोस्त है. सोचने के बात नहीं है. सच में दोस्त है. Now I am giving an example. ये जब बातें करते हैं ना, when they talk, I can guarantee in 70% times when he is talking, he has not finished, he will start answering. You tell me yes or no. What is the meaning? That means you are not listening to me. You are just hearing. You can, whatever he is saying, you thought, okay, समझ गया. Very bad soft skill. You have to listen. Somebody is trying to tell you something, you have to listen. It's a great soft skill. You know, all the very top people I have seen in my life, they listen to me. And then answer. You always can answer. And what happens is that you have to practice it. You have to grow. You can't do it on the first day. Start doing, and then you see the difference. You will be a different type of person. And this is the mantra to go out. Yeah. Our life is like a pyramid. What is that? When you join a job, you are at the bottom. Lot of people. And then it is a pyramid. As you go up, it gradually narrows. That means, come with me. And now you tell me why you should be put at the top or at the upper level. What is your quality? Almost everybody knows the same thing, technologically. Then why you will go up? There are other skills. That's the point. That is what I am trying to tell you. So next, आगे बढ़ो. पहले ही तो बहुत सारे इक्वेशन दिखा दिया ना वो प्रोफेसर ने. हमने कुछ नहीं दिखाया. But एक इक्वेशन दिखाया आपको. Now see, अच्छा 1 to the power 365. What is the answer? Sure. 1.01 to the power 365 का रिजल्ट है. अच्छा, why I am showing you this? I'm कैमरा बैठा थी. 1 to the power 365 means कि 365 days पूरा एक साल. I am doing the same thing. So I started as 1. At the end of the year, I am 1. No change, no improvement. What is 1.01? 1%. Mathematically 1%. Small improvement, but every day. That means I am doing slightly more. So I started with 1. End of the year, 37.78, and this is not 37%. Your improvement is 37 times. It's a huge change. And what you have done? Just a small thing every day. So what is the catch word? Every day. What we do? We do something today, something tomorrow. Oh, very tired. Drop it by. But those who continue, they like that. That after a long time, these people go up. These are the qualities I am telling you, that which will make you go up. Next. I don't know whether you have seen it. Virat Kohli to बहुत सारे देखते हो. Have you seen marathon race? Have you heard a name called Usain Bolt? Yes or no? Yes. Have you seen Usain Bolt running? It's fantastic, right? From start to finish, it's a fantastic. But marathon, as Usain Bolt used to run 100 meters, 200 meters. Marathon is 100 meters. How much? 26 miles. That means almost 42 kilometers. Now 42 kilometers, if you run, can you run like Usain Bolt? No. That is the answer. So, when you will graduate, your age will be 22. Say you will retire at 60. How many years you will work? 38. So, this is a marathon race or a 100-meter race? So, should you run like Usain Bolt? That's a soft skill, you have to learn. They don't run like that tomorrow you have to achieve everything. You have to run a long time in the run. And then only you go up. This is something you have to put it in your head. But we see people running from the day one, and then after some time, they are all very tired and they are not successful. Next. आगे बढ़ो. आगे बढ़ो. One thing, see, this is another mean. See, please remember that fundamentals are most important. So here you see the top one. That fellow is so lucky, so happy, driving a Python. But actual picture is the bottom one. That Python is riding over C++. So therefore, try to get the fundamentals whatever way you are working. Try to get your fundamentals right. That's what I am trying to tell you. आगे बढ़ो इसको छोड़ो. हाँ. अच्छा, you people have all heard the name of Niels Bohr? Sure. Bohr's model of what? Atoms. So Niels Bohr said this. What he said? Just one sentence. And what does it mean? And you know the Stone Age, right? That is human civilization. There was a Stone Age, then Metal Age and all that. So in the Stone Age, everybody used to use only stone. But then people started using metal. So Stone Age is gone. But Stone Age is gone. Is it because there was no stone? No, stones are there. So what happened? That some new idea has come. That it is better to use metal than stone. So what is that? Basically what Niels Bohr is saying? That it is always the idea that matters. So not only that what you are, you know or something, idea that is most important. Next. And the last thing I want to tell you, because you are all going to be engineers, not scientists, forget about it. Even if somebody wants to be scientist, but still remember you are still an engineer. The engineer's job is that it should work, whatever you are doing. Say you are working in a factory, something has gone wrong, your production has stopped, and your boss has called you, hey, go, fix it up. Now will you tell your boss that, okay boss, I will go through the books and etc. 3 days later I will give you a solution. So your job is wrong. So engineer's thing is you have to get it done. Please remember. Then only you will be a good engineer and you will be given value. Otherwise no. Like scientists have different ideas. They can propose theories, etc. But engineers, you have to get it done. You are a software engineer. You have written a big code. And then you see it is not working. So what happens? You are a useless software. You have no value. So please remember this thing, that engineer's job is to get things done. Please remember this. And now it is 5:05. Your bus is approaching. 5:20 people say. I should not stop you from the bus. Because then I have failed in my duty. I started with saying that this is my test of my soft skills, because nobody wanted to hear me. And how many were heard me? Raise your hand. And who have not heard, forget about it. I don't mind. Anybody? सुना है किसी ने? बस कुछ नहीं सुना. चलो. Okay, thank you very much for boys and girls.
Thank you so much, sir, for such an informative and interactive session. We are really delighted for this session. Thank you, sir. Please maintain the silence because the seminar is still on. Anything you like to ask, sir? The forum is open. This session was so interactive, so I think you can interact with what I was saying. Any questions from this section? Then I can give the microphone. Any question from the audience forum? Sir, your session was so interactive, so please delete all the fear and you can ask the question. Buddy. Okay, so now we are at the end of today's seminar. So it was really interesting and informative session for the expert talk we have got from the experts from Jadavpur University, and we are thankful for this seminar. So I'm concluding this seminar, and I would like to share my vote of thanks to the head of the Department of ECE for organizing the one-day seminar, and to all the members of ECE, the students, the participants, and definitely the experts who have been here for their time and given us an opportunity to be a part of this seminar, and for sharing their expert talk in the domain. So thank you so much and have a nice day, and we are concluding the session in today. Thank you so much. Thank you so much.
কৌশিকের ল্যাপটপটা কি বন্ধ করবো? দাঁড়া